Okay, so picking up where we left off, um, so we were looking at electrolyzers. So we were talking about how you make hydrogen, and you can either make it from like natural gas using steam methane forming, or you can make it from water by splitting it apart. Both of those have issues associated with them. Steam methane reformers emit a lot of carbon dioxide, so you need to capture that, which in turn increases the cost of the hydrogen. Um, and electrolyzers use a lot of water, obviously. That water often has to be pure, which takes energy. It also, consumes the water, which could be used for other purposes like agriculture or human consumption and that sort of thing. And also, the the electrodes often contain critical minerals, which may, come from parts of the world that are a little more, some of the more problematic parts of the world, shall we say, and can be quite expensive. So those are kind of the issues with that. Also, obviously, with electrolysis, the carbon intensity of that depends a lot on where you are getting your electricity from. So if you have a very heavily coal-based electrical grid, then you might as well just not do it because you're going to be creating more CO2 than you're trying to abate with the use of the hydrogen. So that's another thing. Now, in terms of cost, this is kind of a low baseline here, but let's imagine that, in the perfect world, you're running electrolyzers generating hydrogen, and the electrolyzers are powered entirely by solar or wind. So this is a very, very low carbon footprint scenario. What would the cost of that hydrogen look like? Because we saw that, well, maybe I'll go back to that slide. Yeah, so for steam methane reforming, if your baseline is $1 per kilogram for hydrogen generation in the US without any carbon capture, adding the carbon capture obviously increases that cost, and the amount of increase depends on basically the cost of natural gas wherever you are. It's a lot more expensive in Europe than it is, say, the Middle East or the United States, because both of those places have much cheaper natural gas. So what about running your electrolyzer completely on solar or wind? Well, you can see here that, this is a color scale based on hydrogen generation cost, and this is in US dollars, I guess 2021 dollars. You can see that in parts of the world that have significant solar or wind resources, so like, the Atacama Desert, the Middle East, Tibet, these are places where it's very sunny and very windy. You can get costs below $1.50 per kilogram. So it is competitive with steam methane reforming with CCUS. But other parts of the world, are not very well suited for that. So, anyway, this just gives you an idea of, kind of what these costs might be if you move to entirely zero carbon electricity. So we'll see where that goes. Now, back on the side of generating hydrogen from organic material, a lot of hydrogen, particularly in China, is made from coal because they have significant coal resources there. And it's done in a process called coal gasification, which you may have heard of. It's also a way of making methane. You can gasify the coal, and then it's obviously burns cleaner than it would in its original form. So just thinking about how coal is made, you start with decaying organic matter, which has a lot of these long chain carbon-based molecules like lignin and cellulose, and sulfur and nitrogen. And then as that stuff gets buried and compressed over time, you lose some of the water, so you go through dehydration, and then there's some chemical changes that happen, including this decarboxylation process, which is the removal of the dangling carboxyl groups from some of these molecules. And then the other thing that happens is that the original material typically consists of aliphatic carbon chains, which means, it's basically what we think of as a typical, hydrocarbon molecule. It's just a long linear chain of carbon atoms. And they change to aromatic, which is more kind of ring-based molecules. And then as you get to higher and higher grades, you lose the methane until you're basically left with almost carbon black at the end of the process. So you can see that there is, a significant difference in how much hydrogen there is in the coal, depending on what grade it is. So this is a typical molecule that you might have in coal, and I'm not even going to try to guess what this is. But the thing that I want to point out here is that a lot of these dangling functional groups contain hydrogen, and that is the hydrogen that you're seeking to extract from the coal. So we've got a lot of these hydroxyl groups. Here's a methyl group over here. What else do we have? Here's an amine. So all of these things, bless you, contain hydrogen. But the thing is, because of these the demethanation processes and also the conversion to aromatic carbon rings, you gradually lose hydrogen as you go to higher and higher grades. So bituminous coal, which is, this one kind of here in the middle, that's got about 5% hydrogen. But then when you go up to anthracite, so when you increase the grade of that coal, it is only 2%. So basically, you want to target lower grade coal for this gasification to make hydrogen, which actually is kind of an interesting thing that, for coal, generally people target anthracite because that has the highest energy content per unit mass because it's been compressed down so much. But there is a lot of, lignite and subbituminous coal around the world, and it could be useful for making hydrogen and other chemicals. So the way that this works, it's a similar process to steam methane reforming. The coal is used both as to power the boiler or to power the steam chamber, and you just have to go through the gasification process to turn that into coal. And then you add steam, do the water gas shift, and then you do the separation of the hydrogen and the CO2. So basically the same thing. Again, it emits a lot of CO2, which is something that you have to think about abating. So just looking at this is a bar graph of CO2 intensity of hydrogen production. And this is looking at the different ways that we generate hydrogen. So at the top here, this is coal gasification. And you can see if you have 90% capture of the CO2 emissions, you can be down around 2 kilograms of CO2 per kilogram of hydrogen. For natural gas at 90% capture rate, it's less carbon intensive because there's one fewer step or one less step in the process because you don't have to gasify the coal. Again, you're not even without CCUS, you're not producing as much CO2. But then with electricity, so this would be hydrolysis. This highlights the point that I was making earlier that the variation in your carbon intensity is very strongly. What am I trying to say? The carbon intensity varies depending on what the source of your electricity is. And to my point, if you have a heavily coal-fired electricity generation system, you can have significantly more CO2 emissions than even steam methane reforming without carbon capture. Okay, so if you're thinking about doing electrolysis to make hydrogen, you have to think very carefully about where you're getting your electricity from. Okay. And in fact, this is kind of in the news right now. So the Inflation Reduction Act has a lot of tax credits and tax incentives built into it for all kinds of low carbon technology. But the one that's being kind of haggled over right now is what's called the 45V tax credits, which are supposed to go to clean hydrogen production. And the Department of Treasury, which would be the ones who actually implement the rules specifying what that is, are having a hard time defining what exactly clean means. And there's, they're proposing all these restrictions about, like, you have to, if you're doing electrolysis, you have to build new renewable generation that's not going to compete on the grid with other end uses of electricity. If you're using intermittent sources, you have to match, I think it's hour for hour, how much generation you have with how much electricity you're actually using. So there's all these restrictions, really to try to get away from this issue here, which is that if you don't do it right and you implement electrolysis at a large scale, you can increase CO2 emissions by a large amount if you're not careful. And so, they're thinking very hard about how to do this. Okay. This is another plot. Now we're looking at cost. And if you are looking at, this is a cost comparison of electrolyzers versus natural gas. Because remember, I said, $1 per kilogram of hydrogen is roughly the benchmark price here in the US for hydrogen made from natural gas without carbon capture. So there's that $1 per kilogram. So the horizontal lines here, that's kind of a bracket of two end members for natural gas price. So they've got $3 per million BTUs and $11. The funny thing is, I think, I should have looked this up. I think right now, natural gas prices in the US are closer to like $2.50. They're quite low. And so that would kick you down here at about the $1 per kilogram line. So you can see that for most ranges of electricity prices up to about $40 per megawatt hour, electrolyzers are cost competitive with steam methane reforming. And if you get really cheap electricity, you can actually have it end up being cheaper than steam methane reforming. So there is, some cost competitiveness there that you could take advantage of. Okay. Now, here's a couple of things that are specific to Texas, but are kind of interesting to think of. So this is a couple of plots that I pulled off of the ERCOT dashboard. For those of you who don't know, ERCOT is the, I'm gonna get this wrong. I always get it wrong. Electric Reliability Council of Texas. They are the organization that oversees the electric grid in most of Texas. And so these are plots of electricity price snapshots for 2 different days. This one here is a hot day in June of 2022. This one over here is a hot and windy day in April of 2021. And the things that you can look at are, you can look for areas where the electricity prices are high, because the way that the market works here is that when there's more demand, the electricity suppliers start charging more money. It's just, it's a supply and demand problem. And so, on a typical hot day in June, you can see there's not a whole lot of variation in supply and demand around the state. And the prices that we're looking at are somewhere between, $50 to $80 per megawatt hour, depending on where you are. But over here, this was, like I said, a hot, windy day in April. And what's really interesting here is that you can see the patterns of where you've got demand versus where you've got supply. So obviously, you're going to have a lot of demand on a hot day in the Houston area. There's a lot of people who live there, a lot of air conditioners, also a lot of industry that consumes electricity. I think it's about 50% of the electricity in Texas that goes to industrial sources. But look at these places where you've actually got negative electricity prices. Up here in the Panhandle and down here in South Texas. And what's interesting about that is those are places that have a lot of wind generating installations, okay? And the problem is a lack of transmission. So if you're generating a ton of electricity down here in South Texas from your wind farms, but you can't get it to Houston where people need the electricity, you are literally going to pay people to take your electrons away. Say, please take this electron, find it a good home, okay? Because there's not enough transmission infrastructure. So that raises an interesting point. If I go back here, so they didn't extend these lines down to negative prices, but you could generate some wicked cheap hydrogen in a situation like this where you've got nowhere else for your electricity to go, okay? And so this is something, we'll come back to this when we talk about underground storage, but this is a concept that is, probably going to be maybe, one of our first viable sources of, clean hydrogen is to take excess electricity generation and use it to run electrolyzers. And then what you do is you pump that hydrogen underground. And this is a plot of oil and gas wells in Texas that could potentially be used for hydrogen storage. And again, there's a good amount of them in South Texas and up here in the Northern Panhandle. So, this could be something we could look at in the future. And I think, like I said, I think you'll see this sort of thing sooner rather than later. Okay. Let's see. Here's another plot here. This is life cycle emissions, and it's plotted here in kilograms of CO2 equivalent per kilograms of hydrogen. So this is really kind of an apples to apples comparison of all the different technologies that you can have, showing, relative to each other what the carbon intensity is. And you can see that, let's see, obviously zero carbon electrolysis and nuclear are going to have a very, very low carbon footprint. And this is a bunch of studies that have done these life cycle analyses. It's just a comparison of them. So obviously those ones come up with very low life cycle assessments. But what's interesting is that you can see that steam methane reforming with carbon capture comes in by some estimates, actually lower than a lot of other, kind of regional grid-based electrolysis solutions. And this is kind of a long way of saying that, if you're thinking about generating, quote unquote, clean hydrogen, you can't just throw out anything that's using, coal or natural gas or anything like that. It is possible to make those low carbon. And so, when you're putting together your suite of solutions for hydrogen generation, it's important to include everything and think very carefully about kind of what these life cycle emissions are, instead of kind of going based on vibes where you say, oh, that generates CO2, that's bad, let's not do that. So anyway, I'm going to get off my soapbox here. Anyway, I had an op-ed about this a couple of weeks ago, so it's kind of fresh in my mind in terms of kind of crankiness. Anyway, okay, enough about that. So I mentioned earlier on that right now we are not producing significant amounts of naturally occurring hydrogen from the subsurface. So basically what you're looking at presently is you have to make your hydrogen using one of the techniques we just talked about. However, I strongly feel that in the next couple of years, you're going to see more and more activity around production of geologic hydrogen. And this has a lot of advantages because if you, think about what this value chain looked like when I showed it to you guys initially, it, had all this nonsense over here on the supply side about how you actually make the hydrogen. If you can just pump it out of the ground, I mean, that simplifies this a whole lot. And then you can just move it to where it needs to go using something similar to like what we currently do with natural gas. We already know how to do that. So the real question is, how do we make this side over here happen? So this is the example that everybody always uses to talk about geologic hydrogen. And it's a little bit of a one-off type thing, but there's a place in Mali, it's called Barakabougou, and they were drilling a water well in 1987. And one of the guys on the drilling rig lit a cigarette, and like there was an explosion. I don't think anybody died, but and they were like, holy cow, what's in this water? And it turns out that they had discovered a 98% pure hydrogen accumulation in the rocks that they were drilling through, which is crazy. And so right now, it's using to provide electricity for the village. And it's not a very high producing well. It's 1,500 cubic meters a day, which is 53,000 cubic feet. So it's not a very big flow. And it's somehow, so if you look at the downhole logs here from the well, so the one to pay attention over here, this is the gas log. So while they're drilling, they're monitoring the composition of the gases that are coming out of the well, and specifically looking for hydrogen. So you can see down here in this zone that they drilled through, they had a big spike in the hydrogen. So that's kind of where the hydrogen is coming from. But they don't know exactly what the source is, and it appears to be continuously recharged because they haven't seen any evidence of pressure depletion, since the wells have been producing. So this is kind of a weird case, but it does kind of prove the point that you can have hydrogen accumulate in the subsurface. So I think we'll leave it at that for today, and I'll go on Wednesday talking more about geologic hydrogen. So I hope you all enjoy the rest of your Monday.